Today's lecture is about the body plots. So we have today's lecture and the next lecture. So today is Wednesday. We will go to the body plots. So we will cover the main things in body plot today's lecture, and then Friday we will finish it. So the first half of Friday lecture to finish the body plots. We will go through just overview. We will not discuss deep details with the time. And then it will be exam 3 written. So we'll return exam 3 in the other half. And we will go through the answers in a quick way. So that's the class X. Then the final exam will be in May 3rd, Wednesday. This is the final exam. It will be at Friday. So final exam will be at 8 a.m. From 8 to 10, 2 hours exam, and it will be in this classroom. I think you can look at the Canvas. I'm not sure if it's not today, maybe by Friday. You can look at Canvas. You will see final exam info. A folder is called final exam info. Then you will see the formula sheets that will be provided to you in the test. I think it will contain 4 pages. And you will see a sample test. Okay, so sample test is just, don't again rely on the sample test for the exam, but you can just test yourself after you finish everything. And I will also encourage you to look at the formula sheets. Okay, any questions? Yes.
Will we get a note card on the final as well?
Yes, a note card still 3 by 5 note card. It can be double-sided, there is no problem, but keep in mind to write your name. And it must be handwritten. So 3 by 5, write your name, double-sided. And in addition to this, there is a notes card or the notes questions formula sheets, 4 pages, 4 pages formula sheet. So you can have, you should have an access to formula sheets soon. Then if make sure don't try the same information that you have in the note sheet in your note card. I mean, you can write whatever you want. Okay. Any other question? Let's start the body plots. So, what's body plots? What's the importance of this? Basically, body plot can be used, or in body plot we are analyzing the magnitude and the phases changes by LTI system in frequency domain. So in other words, it's graphical representation of frequency response. Graphical representation of frequency response. So basically it will tell you there will be a graph for the magnitude, a graph for the angle, so it will tell you how is the performance of the system. And most likely we will add log, or you know that there is the natural algorithm, there is different algorithms, so it will be like log, so it will make a fast to see how the fast change or how the change over varying range of frequency. So like the axis, for example, the frequency axis, it can be, for example, 0, 5, 10, 15, 20, and so on. With this axis, it's very slow to see these changes. But if you want to make it fast axis, we will make the frequency as log, something like that. So with log omega, when we say log, it will be like 0, 10, 100, 1,000, 10,000, etc. So it will be the change that you will see, or the frequency range, it will be faster. So you can look for large variety changes when you use the log. So it's again, so the graphical representation, and it will be used a lot in control systems when you make a design, and as well as in communication as well. So later, when you learn the control systems, advanced control systems, you will learn also other than graphical inputs. You will hear about the body parts. You will learn about Nichols charts. Then there is what else? I think Nyquist as well. Then there is the root locus as well. So you will hear about different topics, different things in frequency. All of these four things that I mentioned are in frequency. But basically, body blocks, it can be as an indication about the response. And then we can use it to select the pole, the design pole. So in the control system, basically, we will control the system by changing the location of the poles. Then these poles will matter when we do the body blocks. So this will affect and impact on the performance or the characteristics. And we can use this a lot later in this way when we design some filters. Low pass filter, band pass filter, high pass filter as well, and as well as different other parts. So there are many applications. Here we didn't have enough time to cover the applications, but I will go only through the foundations or the basics. So later when you hear about the body blocks, okay, at least you have a clue what it is. Then you're going to use it in the future process. Okay, so it's graphical representations. Basically, when we have any system, you will have an input and output. It can be voltage, whatever. So let's assume it's in frequency domain of omega of omega. Then you will have a system. Okay? That system, I can say like, for example, there is AB, and I can make it that system actually as an amplifier, as an example. So amplifier. So in the amplifier, we know that the gain, so AV means voltage gain. So voltage gain. AV of omega equals to V out of omega over Vn of omega. That's an example of the voltage. For any other LTI system, you have inputs, omega, then I will say A system, then V out, then we can say V, not V out, I'm going to say out, other than voltage. So you can say A, which is a transfer function, equal output of omega over input of omega, which is the transfer function. It's the same as the transfer function that we know. Transfer function. Okay? We know how to make a transfer function. Then it's the same. Or you can say, as an application, we have amplifier output, voltage over input voltage, etc. Now, how can we represent this? We know S equals sigma plus J omega. When you have a transfer function as H of S equals sigma plus J omega, then you can substitute sigma equals 0. This yields S equal to J omega. This is actually Fourier transform. Then you can say H of J omega. Okay? So H of J omega, now it is a complex number. Since it's a complex number, it will have magnitude and angle. We have magnitude and angle. Then, for representing how to represent the magnitude, to represent the angle, now we would like also to discuss something like called decibels. Decibels, in other words, we call it dB. So, dB, we have two formulas for it. The first one for power. So we can say it is actually the ratio as a transfer function, output over inputs. For the power, we can say the P out over the Pn in dB, in decibel, will be 10 log P out over P. And log here means the default is base 10, log base 10. keep in mind when you do it in MATLAB, if you write the code log, the default is the natural log. But for us, when we do the math, the nature, if you say log without anything, it is base 10. But when we say ln, log means log base 10. When we say ln, means log base exponential. Okay? But in MATLAB, the situation is different. When you write log, the default is exponential. Okay, so the formula is 10 log P out over P. Okay? The other formula will be discuss the voltage. So we have the voltage formula, the power formula. The voltage, V out over Vn, dB is equal. It is 20 log base 10 V out over Vn. So you can notice that for voltage we will use 20. Power we will use 10. Okay? Why? What's the point of this? How can we prove or why the power is 10 while the voltage is 20? Basically, let's start from the voltage and I'm going to try it step by step. So we have the decibel V out. Or I would say 20 log 10 V out over Vn. Okay? Then I would say I'm gonna make the square. So when I make the square, 20 log 10 V out square or V square. I'm just taking the square root of everything. Okay? Then after that, after you take the square, you can divide by R each part. So the next thing I will say 20 log 10 V out squared over R divided by Vn squared over R. And what you know about this, okay, let me, there's something that I'm missing. Let's fix it here. Here it is 10 times 2 log V out over Vn. Then we will take this, we call for example, A log B equals to B log B power A. Log B power A. So this yields to be overall special square. So we converted this to be square. So 2 log, for example, x will be log x squared. That's what I mean. Then you can distribute the square to be here. This will be 10 because we said the 10 here is here. Then this will be 10 log V out squared over Vn squared. Then divided by R, both sides. Or we can say multiply 1 over R over 1 over R. This is 1 over R. This yields 10 log V out squared over R divided by Vn squared over R. Okay? And we know the power is V squared over R. So this yields to be 10 log base 10 P out over P in. Okay? That's why we have 10 because V out is squared. As a result, we can say that in decibel, dB, 20 log V out over Vn, it's the same as 10 log P out. Okay? So are you using the power or are you using the voltage? If you are using the power, 10 log. If you're using the voltage, 20 log. Okay? Now let's recall some properties for the algorithms. So here we equal A log B. It can be log of B power A. Okay? When you have log of A plus B, it will be log of A plus log B. Okay? Log of B is product. A times B. Log of A over B will be log of A minus log of A. Okay? Then, recall some others properties like log of base 10 of 1, log of 1 every time is 0, because 10 power 0 equal to 1. Then, log 10 base 10 will be 1, because it's actually 10 power 1 equal to 1. So I can say, we call this log of base B, A will be the base B power A. Okay. Then log base 10 of 100 equal to, as a result, this will be 10 power 2, which is 100. Or in other words, how you can find it, you can say this is 10 power 2, then it will be 10 log of 10, 2 log of 10, which will make it 2 times 120. Okay? Other thing other than that, log of 10 power n base 10 will be n log of 10 base 10, which will make it 10 times 1, then the answer will be n. This is similar to 10 power. Okay? Here is like some properties of the now let's assume, or let's put some scenarios in DB. So if assuming the ratio P out over Pn equals to 1, how much this will be in DB? Then in DB, 10 log 10 of 1 will make it 10 times 0, because log of 1 is 0. 10 times 0, which will make it 0. So if the ratio between the output over input power is 1, then it will be 0. How about if the ratio is 10? If the ratio of 10, it will be as B will be 10 log 10, which will make it 10 times 1, then it will be 10. Okay? How about the ratio P out over Pn equal 100? Then in dB, it will be as 10 log 100 base 10. 100 means 2, 10 times 2 will make it 20 dB. Then 1030 dB, and so on. Keep going. This is related to the power. If it is related to the voltage, it will be something different. Here we're just talking about power. So you need to be familiar in how to find these. How about P out over Pn equals to 0.1? So in dB, it will be 10 log 10, 0.1, which means 10 log base 10, 10 power negative 1. This means negative 10 log 10, then it is negative 10 times 1, so the answer will be negative 10. Okay? So if it is 10, this means the input more than the output. Then, another scenario, if P out over Pn equals 2, then what will happen is 10 log base 10, 2, then this is will be approximately around 3. Then, other thing which is only around 3, 10 log base 10, 3, this is actually 4.7. Okay? So from this example, it's very important for you to memorize or know how to find this. Here is the ratio Pm, here is dV for the following. If it is 0.1, this will make it negative 10 dV. If it is 0, this will make it 1 dV. If it is 1, this will make it 10 dV. 2, 3 dV. 3, 4.7 dV. 10, it will be 10 dV. 120. So you need to know this, okay? This is for ratio for the output power. If it is for the voltage, I think you need to double these numbers, just times 2. Okay, example. Assume the ratio P out to Pn equal 5. What should we do? You can say it is 10 log 10, 5. Okay? But I need to use the table that I already provided to you. So assume that this table you already memorized it or you already have it in your note sheet. And in case if you didn't have a calculator, you have a calculator, it should handle this. But I'm going to use the table and see how to find this. So it can be as 10 log 10 5 dV. So it can be written as 10 log 10 of, here it is 10 over 2, 5 is 10 over 2. So which can be written as 10 log base 10, 10 minus 10 log 10 of 2. We know this property. If it's division, it can be subtracted. We distribute this. So it will be 10 log 10, which is 10 dV, minus 10 log 2. Log 2, this is 3 dV. So the answer will be 6. So that's how we can use the analysis method. So this is part A. Part B, if it is 60, the ratio equals to 6. We can say 10 log 10, 6. You can use the calculator to do it, or we can use the techniques, which is 10 log 10, 2 times 3, which is 10 log 10, 2, log 2, plus 10 log of 3, all the base 10. Log of 2, which is 3 dB, log 3, which is 4.7 dB. So the answer will be 7.7. Here's the difference. Then part C, if P out over Pn equals to 8, 8 is actually 2 times 2 times 2, then it is 10 log 2 plus 10 log 2 plus 10 log 2, and all of them is actually 10, which is 3 dB plus 3 dB plus 3 dB. This means 9. Okay, part D, if P out over Pn equals to 9, this is actually 3 by 3. Then it is 3 by 3, this means 4.7 dB, because the log of 10 by 3, 4.7 dB, plus 4.7 dB, so the answer will be 9.4. And so on. Okay? Now, another thing, let's assume we have multi-stage amplifiers, like we have V inputs, here is gain B, then here is V1, and another stage C, here is V out. So, we can say the gain of BW equals to V1 of omega divided by Vn of omega. Then the gain of CW, C of omega, is V out of omega divided by V1 of omega. We know this. Then actually we can say the overall gain A of W equals B of W times C of W. So if you need to find the log because this is voltage, that's why we use 20, because it is voltage. Since it's voltage 20 log base 10 of B of W times C of W, then it will be, since it's multiplication, it can be distributed as some 10 log 10 B of W plus 20 log 10 C of W. Again, why I use 20, not 10? In the previous examples I used 10. Previous examples, those were related to the power, while this example was related to the voltage. Okay? Now, how do we make the analysis when we have, for example, a transfer function, or when we have an example like RC circuits? RC circuits equals response using Bode blocks. Okay, so basically the RC circuits, it is, here is V inputs, yes, whatever the source is, here is R, then we know how to do the Laplace transformation. Assume we have a zero initial condition, so 1 over SC. This is plus minus V out for S, V input for S, and here is I of S. Assuming again, we already convert this from time domain to S domain. How we can do that? You can recall the second exam material, which is Laplace transformation, converting time domain to frequency domain, not phasor, frequency domain. Now, we need to find the transfer function. So basically, the transfer function A, I mentioned sub V because it's voltage, is obvious, which is V of S over V input of S. Now the question is, what's V input of S? What's V of S? We can say like the following. We can say V of S, we can apply Ohm's law, which is I of S times Z of the capacitor. So which is going to be as I of S times 1 over SC. How about the input voltage? I need to, when we use the transfer function, I need to make the input voltage in terms of the current. So we can say also Ohm's law for the input voltages, which is V input of S, well, I of S times Z equivalent. So I of S is actually, again, I of S, Z equivalent, which is 1 over SC plus R. Okay? As a result, the transfer function will V out of S over V input of S, which is going to be 1 over SC times I of S. This is V out, that's what we calculated V out. And here is V in, which is 1 over SC plus R times V I of S. Then we can make shortcut I of S and I of S goes together. Goes away, then multiply by SC over SC. This yields to be 1 over 1 plus RCS. Okay? Then we can assume the resonance frequency, let's omega C, which is a constant, equals to 1 over RC. Something we call it resonance frequency. So whatever about the name, let's call it RC, omega C. So this yields to be 1 over 1 plus S over omega C. Okay? Because omega C 1 over RC. Or in other words, sometimes in circuit analysis we call this tau, or RC tau. This is 1 over tau. So this yields to this is the transfer function. Now we need to do the Bode blocks. The first step is to do like what we did here when you see in the circuit. Convert this circuit into the transfer function. If the transfer function is provided to you, then you can skip this step, you can save more time. But if you don't have the transfer function, you need to find it. Like what we did here, convert the circuit from time domain to S domain, then you can do the analysis. So now In order to do the Bode plots, you need to use Fourier transform. Fourier transform, you will make S equals sigma plus j omega, assume sigma equals 0, this yields S to be j omega. So what you will do in the transfer function for every S, you will substitute j omega. So as a result, I'm going to call it now A v of omega will be 1 over 1 plus j omega over omega c. Okay? Now, since we have this, we need to plot two things. So today's lecture, I will focus more in plotting the magnitude, while next lecture, I think I will go to the angle. So we have a magnitude, then we have angle. So let's discuss the magnitude. So the magnitude in dB, A v omega in dB. Is this one voltage or power? It is voltage, right? So it will be 20 log 10 of AV of omega. I'm going to take the magnitude. So, as a result, this will be 20 log of, the absolute value means the magnitude. Magnitude 1 over 1 plus j omega over omega c. Okay, so we need to find the magnitude of numerator and denominator. So we have, it is 20 log of the magnitude of 1 over the magnitude of 1 plus j omega over omega c. The magnitude of 1 is 1. There is no problem, right? The other thing, which is the magnitude of 1 over plus j omega over omega c. So we can say, since it's division, we can distribute the amplitude, so it will be log of 1, and the magnitude of 1 is 1, subtracted from 20 log of 1 plus j omega over omega c as a magnitude. 20 log of 1, it is 0. Then 20 log of the magnitude, we need to find the magnitude. And how we find the magnitude? As we know, it's the real part squared plus the imaginary part squared, and there's a square root of this. It's from the complex number analysis, which is the square root of real part squared plus imaginary part squared. Okay? Then, when you have, since you have this, you can say it is negative 20 log of 1 squared, which is 1, plus omega over omega c, all of it squared, all of it power 1/2. So 1/2 can be given to the other side. So it will be as negative 10 log of 1 plus omega over omega c, all of it squared. So now let's stop here and try to figure out how we can find this. So we have several cases. Case number 1, when omega way lower than omega c, which is omega c very large. So it will be any number over a large number, any number over infinity will make it 0. As a result, omega over omega c almost equal to 0, when omega c is very large. This yields to be negative 10 log of 1 plus 0, which is negative 10 log of 1, which will make it 0. So in this situation, it will be 0. Second scenario, when the opposites, omega way larger than omega c, which means omega c is very low. As a result, this will, what will happen is, will make omega over omega c very large number, larger than 1. So it can be, for example, 1,000, 1 million, something like that. So the 1 is negligible with respect to this. So we can approximate this to be as, neglect that one, 20 log of omega over omega c squared. I mean, here it's 10. 10 log omega, I'm substituting omega over omega squared, because we assume that one is 0 squared. So the answer will be here we can say multiply by 2, negative 20 log of omega over omega c after removing the square. Then we can do the subtraction, which is negative 20 log of omega plus, because negative will be positive, 20 log of omega c. All of it will be. So it will be as a function, because this one is constant, this one is function. Then the last step, if omega equals to omega c, what will happen? When omega equals to omega c, this makes omega over omega c equal to 1. Then as a result, it will be negative 10 log of 1 plus 1, which will make it negative 10 log of 2, and we said this will be negative 3. So as a result, we can say we have different scenarios. We can say we have omega, or different parts, which is dB here in this circuit. The overall function 1 for 1 plus j omega over omega c. For plotting the magnitudes, we have when omega way less than omega c, then it will be rounded as 0. Omega equal omega c, it will be negative 3 dB. When omega way larger than omega c, it will be negative 20 log 10 omega plus 20 log omega c. As a result, as things looks like negative dB of omega, whatever the value, plus a constant c. So there's a constant. So when we plot this, try to plot the magnitude dB here, you will see here is omega, maybe per second, and here is the magnitude in dB. So for omega, you will see that the critical point is omega c. At omega c, the actual plot, it will be at negative 3. Then what's happening? Before omega c, when it is very low, it will come from 0. When it is very high, it will go toward a slope negative 20. That's what's happening. That's the actual. So let me just try to fix this. So we can see that there is. That's what the waveform looks like. So doing this analysis every time will take so long. So can we figure out a way to make it much easier? Because this one is close to 0, and it will be at least. We can approximate it as follows. We can say here's the approximation. Before omega c it is 0. After omega c it will be negative 20. So that's what we will consider. So we will consider this. Okay? We will not consider omega c will be negative 3 dB. We will consider omega c is the critical frequency, where it is the amplitude response will matter. This is equivalent to low pass filter, such that there's low pass filter. So the frequencies lower than omega c will pass, frequencies after omega c will not pass. Okay. Now, as a result, we can use this result as a result. we have pole and zero effects. So we have pole effect when we have 1 over 1 plus j omega over omega c. After you substitute the pole every s by j omega and try to simplify it to be in this formula, so what will happen? This one will provide negative 20 dB slope and activated at omega c. And again, here we will use only approximated. So, here's our plot. Anything is omega, here is omega. So we can say at omega c, what will happen? Everything for omega c will be 0. At omega c, it will be negative 20 with this slope. Then we have the other thing, which is zero effects. What the zero effect will be as 1 plus j omega over omega c. This one provides positive 20 dB per decay slope activated at omega c. So as a result, this here is a root omega, here is omega, and here is omega c. Then it will be activated. It will be 0 before omega c. After that, it will be activated omega 20 dB. Okay. So when you have a 0, it will make it positive plus 20. Will make it positive. Slope with pole will make it negative, but this will be activated at omega c at the critical frequency. That's the overall. So let's assume this example. Assume 1 over plus we have 1 pole and 1 0. 1 over omega c and 1 0 1 j omega over omega c2. So we have omega c1, we have omega c2. So let's consider case 1 when omega c2 larger than omega c1. So what will happen? Here is the plots. Here is omega c1, here is omega c2. Omega c1, where the 0 will be activated. So 0 means will make positive 20 dB per decay. Before omega c, everything is 0. Then at omega c2, the pole will be activated. So it will be activated at omega c2, and what will happen? It will make it from negative 20, it's positive 20, then add a negative 20, will make it 0. So the slope will be 0, then it will make it constant. Because plus 20 minus 20 will cancel each other, which will make it 0. So you can say that the pole and the 0 can cancel their effects after a certain frequency, depending on where is the critical frequency. We have another case, case 2. If omega c 1 larger than omega c2. Basically, in this plot, you will have omega c 2 here, then omega c1 here. So the first thing before omega c2, everything was 0. At omega c2 associated with the pole. Pole means negative 20 dB per decay. Then at omega c1, it will be activated at 0. So it was negative 20 plus 20 will make it 0 dB per decay. Okay? Here is omega. Here is omega. Then the last case, if omega c1 equals omega c2, what will happen? At omega c1 equals omega c2, this yields, before them that is 0, After done that, it will remain 0 because negative 20 plus 20 equal to 0. So there will be no effects. Or in other words, the transfer function will equal to 1 and 20 log 1 will make it 0. This is incorrect. Okay? Does this make sense? So the overall thoughts, whenever you have a 0, this will make a positive slope. Whenever you have a non-zero, this will make it a negative. Okay? Okay, so now we don't have enough time to cover next, but I would say I was recording.